At the center of our galaxy lies a region known as Sagittarius A star, widely believed to be the location of a supermassive black hole about 4 million times the mass of our Sun. But while there is insurmountable evidence that this black hole actually exists, there is some skepticism surrounding it. That's because, like all black holes, astronomers have yet to observe it directly to confirm its existence. But the race is on to be the first. This is Cerro Paranal in the Atacama Desert in northern Chile. At around 2,600 meters above sea level, the desert sits above much of the moisture in Earth's atmosphere, making it one of the driest places on Earth, an ideal place for building one of the world's most powerful telescopes. But observing a supermassive black hole in the middle of the Milky Way takes more than just one powerful telescope in near-perfect conditions. It takes several. The Very Large Telescope Array, or VLT for short, sits in the Atacama Desert and uses 4 massive optical telescopes to study the goings-on in Sagittarius A star.
We are roughly 30,000 light years away from this center of our galaxy in a spiral arm. But we can very well study this region of the galactic center.
Astronomers are able to utilize the power of all 4 telescopes in the VLT array to explore and understand the Milky Way using a technique called interferometry. Normally, the resolution of an optical telescope is limited by the size of the main mirror inside it. The bigger the mirror, the more light can be picked up, the more detail you can see. But if we wanted to see the depths of the Milky Way with just one telescope, we would have to build a 100-meter wide mirror, which would be technically impossible. But with interferometry, the light beams captured by all 4 optical telescopes in the VLT array can be combined using a computer. This basically creates a single telescope with a virtual mirror as large as the furthest dishes are apart from each other. This takes care of the impossible-to-build gigantic mirror.
So we're using a very fundamental property of light, and so in this case we can recreate almost the resolution of a 100-meter telescope.
This means astronomers like Oliver can use the VLT to study the center of our galaxy, including activities surrounding the supermassive black hole.
So we know that this black hole is actually not black, so that means it once in a while it flares. So we see it kind of brightening and darkening, and we believe that must be some matter which is falling in. If we can study these motions which happen so close to the black hole, we have a direct probe of the space-time close to the black hole. And so in this way we have a direct test of general relativity in one of the most extreme environments which you can find in the universe.
But as much as it seems like the VLT is sitting alone in this vast dry desert, it actually has a neighbor. This is the Atacama Large Millimeter Array, also known as ALMA. It is a radio telescope comprised of 66 state-of-the-art antennas, equipped with receivers so sensitive they can pick out a golf ball 9 miles away. And by using interferometry to harness all 66 antennas, ALMA is able to study regions of space that the optical VLT cannot, notably the coldest and dimmest objects in our universe, like the center of a supermassive black hole, or where stars are formed.
ALMA is opening this window that is the cold matter in the universe, where the stars are forming in the cold matter. So in the optical is difficult, much more difficult to do interferometry. You cannot go to investigate, for example, cold matter because you cannot see it. ALMA can go behind this limitation and can go to see where the stars are formed. So in this respect, ALMA is opening to me a completely new horizons. You can see details that are better than what space telescope can observe in space, out of the atmosphere.
But what's really exciting for astronomers like Gianni is that ALMA is actually a smaller piece of a much, much larger puzzle. In 2015, the array became part of the Event Horizon Telescope, a project that utilizes interferometry to unite a network of radio telescopes from around the world. Essentially, the EHT is a virtual radio telescope the size of our planet, making it the largest ground-based astronomical project in existence. In 2017, the EHT completed 5 nights of observations and may have finally observed the event horizon of the supermassive black hole at Sagittarius A star, which is the boundary marking the limits of the black hole beyond which nothing can escape, which has never been done before, and could provide further evidence that this black hole at the center of our galaxy exists. Thanks for watching, and make sure to follow Focal Point so you can catch the latest innovations and scientific breakthroughs. Next episode, we'll look at how recently declassified documents are changing the way we think about nuclear bomb blasts. Don't forget to share this video and let us know what you think in the comments below.